but you probably won't win because it's only a 4% chance. So now that we have the whole probability distribution, we'll take each prize amount, multiply it by its probability, and add those all up. And that will give us the expected winnings. And that will be in the spreadsheet because this is a lot of work. It's not fun to do by hand. And what we'll find is the amount of money you're expected to win is less than you'll pay. That's how the lottery makes money. They give out a lot of money, but not very often. They keep 96% of the $2 that people pay. Like we did in chapter 2, when we were describing a distribution, we found measures of center like the mean. We could also find the median. We could talk about shape, and we could talk about variability. We can do the same thing with probability distributions. We've found the mean. We can also find medians. We can find modes. We can find standard deviations if we want. We'll probably skip over standard deviation because it's not that useful to do by hand, but we'll let the calculator do it for us later. So here's another example of a probability distribution. This is something about passing your driver's ed test. So what we have is how many tries did it take the person to pass? So people could pass on their first attempt up to their 5th attempt. And we've measured how often or how many people required each attempt. So 30 people needed 1 attempt, 10 people needed 2, 2 people needed 5. So in total we're talking about 50 people. So what we can do is we can take each frequency divided by the total to give us the probability. So 60% of people, 0.6, needed 1 attempt, 20% needed 2, etc. And all of those probabilities add up to 1. So if we think about the data, what we would observe, all of our counts, all of our numbers of attempts, we would have 30 ones, 10 twos, 3 fives, 3 fours, 5 threes, 3 fours, and 2 fives. So we could use this data to find a mean, a median, a mode, or we can visualize the probability distribution. It's just a bar chart. That's another way of visualizing this. Because our variable we can think of as being quantitative discrete. It's only from 1 to 5. That's it. So the bar chart would look like this. So again, we can see most often, 60% of the time, someone would just need 1 attempt. So if we want to find the mean, we can use the new formula. So that says take each of your values, so we start with 1, times its probability, times 0.6. And we add up all of them. So 2 times 0.2, plus 3 times 0.1, plus 4 times 0.06, plus 5 times 0.04. So if we do that algebra, or that arithmetic, it works out to be 1.74 attempts on average. So this is sort of weird as we try to think about this. If we randomly picked one of these people, we would expect that they needed 1.74 attempts to pass. Well, you can't do 1.74 attempts. You can do 1, you can do 2, you can do 5, but you can't do 1.74. So the mean doesn't have to be one of our values of the variable. The way that you interpret this is that some people require 1 attempt, other people require more than 1, and that it evens out, it averages out at 1.74. It doesn't have to be an actual observable value. Now the median and the mode do have to be an observed value. They do have to be one of the values of your variable. So when we think about finding the median, it has the same interpretation. Which value is at the halfway point? So half of people require less than this number of attempts, and half of people require more than this number of attempts. So we need to figure out how many attempts that is. So since we have the observed data and it's already in order, it's kind of easy to see that the halfway point is somewhere like here. So it's at 1. So the median is 1 attempt. 50% of people require 1 attempt or fewer, which there is no fewer. 50% of people require 1 attempt or more. This is the halfway point, 1 attempt. Well, if we didn't have the data, how could we get that from the probability distribution? So what we have to look at are the probabilities. And what we're interested in is, where do we reach or exceed 50%? So if we start off in the first possibility, 1 attempt, we see that that's already 60% of the values. So somewhere in here we've surpassed the 50% mark. So again, this is telling us that 1 attempt is the median. Well, what if you started at the other end of the distribution? 5 attempts is only 4 people. Well, 5 attempts is only 4% of the distribution. That's not the median. We need to reach 50%. So we also move into 4 attempts. So that's an extra 6%. So in total, we've taken up 10% of the distribution. We still haven't reached the halfway point. Move into 3, that's another 10, so that's up to 20%. Still not there. Move into 2, there's another 20%. That's at 40%, so we're getting close to 50, but we still haven't found the median. So then we have to move into 1. So somewhere inside the 1 category, we'll surpass the 50%. Visually, you can sort of think about filling up these bars with water or something. I don't know. So in total, we're going to need 1 gallon to fill up all the bars. So what we're interested in is, when do we use up half of our gallon? So as we start filling up the first bar, somewhere up in here, we've reached 50%. We've used half the gallon. So since we're inside the first bar, 1, the median is 1. If you start at the other end, it's the same process. We've used 4% of our gallon plus 6%, so we've used 10% of the gallon, 20% of our gallon, 40% of our gallon. So we have to start filling up bar 1, and then somewhere again within bar 1 we would use half the gallon. So that's a visual way to think about the median. It's which value of your random variable makes up 50% of the distribution. Or, more generally, half of your values will be less than your median value, half will be greater. The mode is simpler. Which value of your random variable occurs most often? So how many attempts is someone most likely to have? And again, that's 1, because that was 60%. The most common outcome, the most common number of attempts was 1. There are formulas to find variance and standard deviation. We're going to skip this. It's really not worth doing by hand. These formulas are kind of ugly. I've never had to do these by hand, so I'm not going to make you. But there is a way to find the variance and standard deviation of a probability distribution. So here's another example. We can find the mean, median, and mode. maybe it was obvious, but if you would like to try these on your own before I go through them, you can just pause the video. So just keep that in mind. So we have a probability distribution. We're measuring X, the number of imperfections in some fabric. So how many problem areas do we see? So within any given length of fabric, we could have no problems, 1 imperfection, all the way up to 4 imperfections. And we're given each of their probabilities. So in 41% of our sampled sections of the 10-meter chunks we look at, 41% of them will have no errors. 37% will have 1, etc. So we want to find the mean, median, and mode, and we'll skip standard deviation. So for the mean, again, you take each X, multiply it by its probability, and add them all up. So we have 0 times 0.41, 1 times 0.37, etc. If you do that arithmetic, you'll get 0.88. So the way that you would interpret this would be something like, on average, because this is an average, there will be 0.88 imperfections per 10 meters of a synthetic fabric. So like before, this doesn't have to be an observed value. This is saying sometimes we'll get 0, sometimes we'll have 1 or more. They don't occur equally often, so it balances out about 0.88. So since the fewest number of imperfections we could have is 0, and this average is closest to 1, this is telling us most of the probability lies in 1 or more imperfections, because this value is closer to the 1, 2, 3, 4 side than it is the 0 side. And that's true from the probabilities. 41% is here, so that means 59% are on 1, 2, 3, and 4. So that's where the majority is. It pools the average towards 1, 2, 3, 4. For the median, we're asking half of the time we will have this number of imperfections or less, and half of the time we'll have this number of imperfections or more. So we need to figure out how many imperfections that is. So we see that 41% of the time we'll have 0, so we haven't reached the halfway point yet. An additional 37% of the time we'll have 1 imperfection. So inside this 1 imperfection category, we've surpassed the 50% mark. And we would get to the same spot going from the opposite direction. 1% of the time we'll have 4, plus 5, so 6%, we could have 3 or 4. 22%, we could have 2, 3, or 4. 22 plus 37 is, what's that, 59? So 59% of the time you could have 1 through 4, so we've passed that 50% mark once we moved into the 1 category. The mode, 0 imperfections. 0 imperfections happen most often, 41% of the time. Every other imperfection happens less often. There's less of a chance to see those. Okay. So now on page 8, we get to the fun stuff. We're introducing a special type of probability distribution. When you make certain assumptions and you measure certain things, patterns can arise in your probability distributions. People noticed these patterns in the past, and they developed the math behind what generates those patterns. And they gave those distributions special names. So we're going to introduce a distribution here called the binomial.